All of you look at this picture. This is a compass having a magnetic needle, and one more here. This is the battery, and here two wooden holders, and this is the conducting wire is connected to a battery. When the battery is on, electric current is passes through the battery. You see the circuit diagram. What happens when the current is passes through it? The magnetic needle get deflect. That is wondering why the magnetic needle get deflect even there is no magnet. We know that the magnetic needle deflect only in the magnetic field. But in 1820, accidentally it was discovered that when the electric current is passes through the circuit, when we place a magnetic needle very near to it, it get deflect. This was the first time stated by the German scientist by name Christian Ørsted. He is Hans Christian Ørsted. His contributions are in the field of mathematics and physics. He was the first time show that there is a relationship between electricity and magnetism. This technique is nowadays helps in radio, television and fiber optics. Now we study magnetic field due to a current carrying conductor. In this video, first of all, we discuss about the magnetic field due to current through a straight conductor. In my next video, you will see magnetic field due to a current through a circular loop, and then magnetic field due to a current in a solenoid. Now let us discuss about magnetic field due to a current through a straight conductor. Look here, AB is a straight conductor and one end of the conductor is connected to a positive terminal of the battery, and then the negative terminal of the battery is connected to a key, and the other end of the key is connected to a B, that is a straight conductor. And one more, a square shaped cardboard is fixed in the middle of the straight conductor, and some iron fillings are spread on the cardboard, and then close the key. Electric current is passes through this straight conductor. What happen then? These iron fillings are arrange themselves certain pattern, that is certain patterns like that. All the iron fillings are in the form of a circular rings. All the circles are having a common center, that is called as a concentric circles. Now let us discuss about the properties when magnetic field due to a current through a straight conductor. Let us discuss one by one. Okay, first property. Here you see this is a straight conductor. Here the circuit connections are there. When we spread the iron fillings on the cardboard, what happen? All the iron fillings, the magnetic field lines align themselves in a pattern of a concentric circle around the current carrying conductor. This is the first property. Second property, here you see this is the current carrying conductor, and here there are many magnetic field lines in the form of a circles. These circles are called as a concentric circles. These circles are larger and larger as we move away from this current carrying straight conductor. And now third property, if you want to increase the magnetic field around the straight conductor, only if we increase the current flowing in the straight conductor is increase. See, fourth property. This is the current carrying conductor. These are all the circles, concentric circles. This is the first circle. It is very near to a straight conductor, and this is the last circle. This is away from the straight conductor. The first circle, near the first circle, the magnetic field is strong compared to the last circle. That is nothing but the magnetic field produced by the straight conductor decreases as the distance from it is increased. Now, once again, now about magnetic field due to current through a straight conductor, its properties. Number 1. Magnetic field lines align themselves in a pattern of concentric circles around the current carrying conductor. That is the first property. And then second property, these concentric circles representing the magnetic field around that particular conductor became larger and larger as we move away from it. And then the third property, magnitude of the magnetic field produced at a given point increases as current through the wire is increased. And the fourth one is the magnetic field produced by a given current in a conductor decreases as the distance from it increase. Look here. This is a straight conductor showing arrow mark that shows the current is flowing from the top of the conductor towards the bottom, and here a cardboard having many circles. That circles is nothing but a magnetic field lines, and here on the magnetic field lines some arrow marks are there. That is nothing but the direction of a magnetic field line. Now you see the direction of the magnetic field line can be studied by some rule. That rule is called right hand thumb rule. Just imagine you are holding a straight current carrying conductor in your right hand like this. The thumb shows the direction of the current and remaining fingers which are showing the direction of a magnetic field. Here the current is flowing upward. The thumb shows direction of current, and you see the magnetic field, its direction, it is outward moving. And one more, here you see a picture on your right side that shows the direction of the current from the top to down. The thumb shows downward direction, the current direction, and the magnetic field, that is inward flow of a magnetic field direction. Okay, thank you for watching this video. In my next video, you will see the current passes through in a coil and its nature of the magnetic field, and then the current will be passes through in solenoid and its nature of a magnetic field. Thank you.